Hi, class. Welcome back. We are still on the kidney, and we're going to be looking at the blood supply. And this is an important concept to grasp because it helps you understand a little bit about how blood gets into the nephron through from the abdominal aorta into the renal artery and into that microcirculation of the kidneys. So the kidneys, although the kidneys constitute less than 0.5% of the total body mass, it's going to receive about a quarter of the resting cardiac output. That's a lot. In terms of nerve supply, the nerves are composed of the sympathetic outflow, the sympathetics. Remember, fight or flight response. When the sympathetics are activated, the blood vessels constrict. When blood vessels constrict, it drives pressure. It drives and increases that blood pressure. So that's what's involved in regulating the blood flow through the kidneys. So let's focus on some of these terms. We can follow it here. We can also follow it off to the right. Now, remember the abdominal aorta is what gives life to that renal artery. So right here, let's change this. Let me just change the color. I'm going to make this color. Okay. So we're going to start here at that renal artery. So the abdominal aorta has a branch coming off of it called the renal artery. Right after the renal artery, so let's call that number one. Right after the renal artery, the segmental artery is number two. Now, after the segmental, it's going to branch this direction in between the pyramids. And in between the pyramids, we're going to call these number three interlobar arteries. So again, we have renal artery, segmental artery. After the segmental, that artery is going to continue where the renal columns are between each pyramid into the interlobar. The interlobar is going to come up and it's going to go and follow the base of the pyramid. It's going to create an arc around the arc of the pyramid. That arc is called the arcuate artery. That's number four, the arcuate. Now, the arcuate, which goes over the base of each of these pyramids, has little tiny branches that come off of it. These very small little arteries that come off and they radiate into this renal cortex. So since these arteries radiate into the cortex region, we can call that number five, cortical radiate artery. What are the cortical radiates? Well, it's the arcuate has extensions that radiate into the cortex. Since it radiates into the cortex, we can call it the cortical radiate artery. So far, we had renal artery to the segmental artery to the interlobar artery to the arcuate artery into the cortical radiate. Now we're going to focus, I'm going to box this in right here. Afferent arterial, glomerular glomerular capillaries, and efferent arterial. I want to focus on that for a second. So in this right here, I'm just going to circle this yellow tubular system. Remember that yellow tubular system? That's called the nephron. And we have to try and drive the blood into the nephron. Right? So how do we get the blood from here into what we see up here, the nephron? Right? All the yellow stuff are parts of the nephron. The red and the purple, those are blood vessels. Okay, so We left off at the cortical radiate. The cortical radiate is going to branch into a vessel called, I'm going to put it in a triangle, just a little different, the afferent arteriole, which is right here, number 6. Afferent arteriole. You see that right here? The afferent arteriole comes in to create this capillary cluster called the glomerulus, number 7. This capillary cluster is called the glomerulus. Here it's referred to as the capillary or glomerular capillaries. And then this blood vessel coming out of it is called, number 8, the efferent arteriole. Number 8, efferent arteriole. So again, we have an afferent arteriole coming in to this glomerulus and an efferent arteriole coming out. Afferent goes in, efferent comes out. The other major difference between the afferent and efferent arteriole, I'm going to blow this structure up right here. So let's say we have something like this, and we're going to have large blood vessel coming in, thin blood vessel, and we're going to have this glomerulus here. So this is the afferent arteriole bringing blood in into the, I'll put a G here, glomerulus, and then here coming out, that's the efferent arteriole. The big difference between the afferent arteriole and the efferent arteriole is the diameter of the blood vessels. Notice the diameter of the afferent arteriole is much, much wider than the diameter of the efferent arteriole. And the innate intelligence of the body does this for a very important reason, because it's driving blood in faster into this glomerular region than it can leave. If it's coming in faster than it can leave, that means that blood is going to hang out here a little bit longer, right? It's coming in faster than it can exit. That means you get this little stagnation or this slowing down of exiting of blood. It comes in faster than it can leave. It creates this filtration time, this glomerular filtration rate. This glomerular filtration rate takes place because you have afferent arteriole bringing it in, efferent arteriole bringing it out, but it's not bringing it out, the blood, as fast as it's bringing it. That's the key. And when you have the stagnation taking place, or the slowing effect, this slowing effect allows this filtration to take place. So it can pull out some of the impurities from the blood and bring it into this nephron, into this tubular system. And when it filters it through this tubular system, it can pull out all the impurities into the minor calyx, major calyx, renal, pelvis, ureter. Okay? Hopefully that made a little bit of sense. And I'm going to go through this a few more times, but just want to introduce this concept of how the blood gets into this glomerulus. The glomerulus is housed in this structure called, let's see if I can bring it right here. It's called the renal corpuscle. Renal corpuscle, which is also referred to as Bowman's capsule. What is Bowman's capsule, or the renal corpuscle? It's this round yellow sphere, this ball, this yellow ball right here, that's housing what's inside that renal corpuscle, or what's inside the Bowman's capsule, is the glomerulus. Okay, so what I want to do here is just show you, here is the afferent arteriole. And then here's the much thinner, the efferent. So this is the afferent arteriole. Here's the efferent arteriole. And then let me just change the color here for a second. Let's make right in here, right? We'll call that the G for glomerulus, okay? And let's call this Bowman's capsule, aka renal corpuscle. So this, it's just cut, right? I just have it cut so you can see what's inside. This is the Bowman's capsule that houses the glomerulus, also known as the renal corpuscle. So far, so good. All right, so now, let me give you some great info here. So now, right after we have blood coming in this way at a faster rate than it can exit, so it's coming in faster than it can leave, so the blood is slowing down a little bit and allows the glomerulus in here to filter, and it's going to pull out whatever it wants to get rid of into the very first part of this tubular system called the proximal convoluted tubule. The proximal convoluted tubule, or the PCT, proximal convoluted tubule. So the filtrate is pulled out, whatever the body is trying to get rid of, it's pulled in through here into this proximal, into the beginning, the proximal convoluted tubule. And then we have this interesting loop that looks like this. This is called the loop of Henle, which we see right here, right? So we did the afferent arteriole into the glomerulus, into this glomerular capsular space, into the proximal convoluted tubule, right? So it's going this direction. We're coming in here through the proximal convoluted tubule. Then it goes down this way. It descends into the loop of Henle. This is the loop. Then it comes up. It ascends. Sometimes they call this the descending limb, and they call this the ascending limb of the loop of Henle. Then we're going to create another convoluted section. If this is the proximal convoluted tubule, then maybe we should call this the distal convoluted tubule, which is the DCT, the distal convoluted tubule. This is all parts of the nephron. What we're looking at here, these are all different parts of the nephron. After this distal convoluted tubule, it's going to lead into a collecting duct, which is here, a collecting duct. There are many different collecting tubules, which are just branches that lead into the collecting duct. And then once we're here, this is all going to be, let me see if I can change the color. Watch this. It's going to make sense here for you, I promise. So then right here, that's the renal pyramid. And what do we have at the base, the apex of the renal pyramid? Well, the papillary duct. And then after the papillary duct, it leads into the minor calyx, major calyx, renal, pelvis, ureter. Okay, so why did I feel the need to draw out this nephron? Well, because we're talking about the blood supply, We started here at the abdominal aorta, leading into the renal artery, into the segmental, into the interlobar, into the arcuate, into the cortical radiate, and the cortical radiate. Remember, I made this box because these are kind of like the beginning of that nephron. So it's leading into the afferent arteriole to the glomerulus. And this structure right here, what we're looking at right there, that's the beginning of where that filtration is going to take place, because it's going to pull out whatever it wants to get rid of. It's going to bring through that tubular system, the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, to eventually excrete out. Okay? And just as we have the arterial system, we also have the venous system. Same structures, right? Like if we had a renal artery, you have a renal vein. We had interlobar arteries, there's interlobar veins. There's arcuate arteries, there's arcuate veins. There's cortical radiate artery, there's a cortical radiate vein. These peritubulars, the peritubulars are the structures that surround the nephron and the different tubules, because the body could be temperamental, meaning maybe at one point it wanted to excrete some of that glucose and some of that water and some of that calcium. But then at the last minute, because maybe you're doing intermittent fasting and you're not haven't eaten in a while, the body says, hey, whoa, hold up. We don't want to pee that out anymore. Let's reabsorb it. Let's put it back into circulation so it could bring it back into the peritubular system. Okay. Now, this picture here is starting us. Remember the abdominal aorta, renal artery, segmental artery. Now it's picking it up here at the interlobar artery. So the interlobars are located between the pyramids in that renal column. So here's an interlobar that's going to create the arcuate artery. Here's the arc. The arc of the pyramid is the arcuate. Off the arcuate, we have an artery that radiates into the cortex. So now it's the cortical radiate. Here's the cortical radiate artery. You have interlobar artery, arcuate artery. Off the arcuate artery, we have the cortical radiate artery. Now, off the cortical radiate, that's where the afferent arteriole, the glomerulus, and the efferent arteriole exist. So, afferent arteriole, that's this or this, that leads into that Bowman's capsule. And what's housed in the Bowman's capsule is the glomerulus. And you have blood coming in faster than it can leave, and then it's pulled. In this case, now it's all purple. The purple is the nephron, and it's going to have those same parts. The same parts, the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. Right, so here's the flow: abdominal aorta to the renal artery, to the segmental artery, to the interlobar, to the arcuate, to the cortical radiates. Okay, now from the cortical radiate, you have the afferent arteriole coming into the glomerulus and the efferent arteriole coming out. Now you have the peritubulars. I'm going to show you where they are. And now we're back into the venule system, the exact same structures, but on the venous side. There's a cortical radiate artery, cortical radiate vein, arcuate artery, arcuate vein, interlobar artery, interlobar vein, renal artery, renal vein, and it brings it back into the inferior vena cava. Okay, so we'll go through that linear structure again. Okay, Okay, so I'm going to draw this out here one more time just for a good review. So let's draw this Bowman's capsule first, like this. And we'll make this like that. Okay, then we'll do this loop. And then we'll make the squigglies again, like that. And then we'll make these little branches coming in. Okay, and let's make this right here, just so we have an idea as to what we're looking at. That's the renal pyramid. Okay, and then here'll be the papilla. All right, so now we have afferent arterial bringing blood into the glomerulus, which is housed by the Bowman's capsule. And then we have the much smaller diameter bringing blood this way, efferent arterial. So blood's coming in through this large diameter vessel. It's coming in really, really hard and fast, but it can leave very slow. So it pulls it into this space. All the debris that we're trying to pull out will eventually come out into this direction. This is our proximal convoluted tubule. Here's our loop. So that would be the loop of Henle. And everything's coming this way, right? So this is our descending limb, and then it's coming up. So that's our ascending limb of the loop of Henle. So there's a descending limb of the loop of Henle, there's an ascending limb of the loop of Henle, and that's the loop of Henle. So if you ever hear people that have blood pressure issues, some of them are on drugs called loop diuretics. Those loop diuretics target this part of the nephron where there's a lot of salt and water exchange right in here. Right, so there's a proximal convoluted tubule, you have the loop of Henle, then we have the distal convoluted tubule. This is the distal convoluted tubule. This is the proximal convoluted. This is the distal convoluted. Then we have connecting tubules. These are connecting tubules that lead into the collecting duct. This is the collecting duct. And eventually that collecting duct leads right into that papillary region or the papillary duct. And then it goes into that minor calyx, major calyx, renal, pelvis, ureter. Okay. Now, I just want to point something out real quick, just to lay this out, because it's going to come, not to haunt us, but we're going to come to revisit this in a little bit. I draw this out in a very linear fashion, just so this kind of makes sense in terms of proximal and distal, right? The further away from the glomerulus or the Bowman's capsule, right? When you're right next to it, you're proximal, and when you're further away from it, it's distal, right? This is the direction that things are traveling. Now, this is going to allow for excretion, right? Because you're urinating it out. But throughout this entire area, throughout here, there's going to be blood vessels surrounding the proximal convoluted tubule. There's going to be blood vessels here surrounding the loop of Henle. There's going to be blood vessels around the distal convoluted tubule, and there's even going to be blood vessels all through here surrounding the collecting duct. And the reason why I say that is if you have blood vessels here, this is going to allow stuff that maybe you are going to excrete out, and it's going to say, hey, I don't want to excrete it out. Let's reabsorb it back into circulation. And it can do that at any level of the nephron. So you were going to excrete it, but now you're going to reabsorb it. And maybe you had stuff in your blood vessels over here that your body doesn't want anymore, and now it can secrete it. It can secrete it from the blood vessels into the tubular system so that it can be excreted. So this is where you have all those peritubular capillaries, right? They're peritubular, meaning around the tubules. So at any point of the nephron, your body can make a decision where, hey, let's get rid of it, or hey, let's reabsorb it. Okay, I wanted to point that out to you. The other thing I want to point out is although I'm showing the distal convoluted tubule over here, the distal convoluted tubule is so convoluted, eventually it will find its way. It will find its way, and I'm going to change the color here. It's going to find its way right here, back. I'll make a bunch of these like cuboidal cells here. The distal convoluted tubule is going to be so convoluted, it's going to make so many twists and turns, it's going to find its way to approach the Bowman's capsule right between the afferent and efferent arteriole. This is still the distal convoluted tubule. And it's a really important area of the distal convoluted tubule because within this area, there's something called the juxtaglomerular complex and juxtaglomerular cells. And right within this region where we have the juxtaglomerular cells and the juxtaglomerular complex, there's a bunch of receptors here that are saying, hey, what's the blood volume like and what's the blood pressure, so that the body can release renin and erythropoietin if it needs to increase blood volume and blood pressure. That happens right here. Okay, so the structural and functional unit of the kidney is called the nephron, and it's responsible for forming urine. And the main structures are the glomerulus and the renal tubules. The renal tubules being the proximal convoluted tubule, the distal convoluted tubule, and the loop of Henle. Those are the tubules. So very simply put, we have blood with waste coming in through that renal artery into the segmental artery, into the interlobar artery, into the arcuate artery, into the cortical radiate artery, into the afferent arteriole, into the glomerulus, right? So all that stuff is coming in here to eventually say, all right, right here is that glomerulus, and it's going to pull out all the debris and eventually push it through the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, collecting duct to form urine. And all the good stuff can be returned into the venous system, which is blood without the wastes, because you've already gotten rid of it through the urine. So the arteries bring in the blood with the wastes, and then the veins return the blood without the wastes. So the basic function of the kidney in terms of the nephron, it's responsible for what we see here on the right. Really important, it filters, it's going to reabsorb, it's going to secrete and excrete. And if you look at the numbers, it shows you right here, look at this, here's the afferent arteriole coming in into the glomerulus, and then here's the efferent arteriole leading away. It comes in faster than it can leave, and as it comes in, it allows for this glomerular filtration to take place, which is number one. the glomerular filtration. Then number two, it can reabsorb. It's a great visual. This is an awesome visual. It's going to say, hey, we don't want to get rid of this, so let's reabsorb it. This is good stuff. I don't want to urinate it out. Let's hold on to it. But sometimes whatever's in the vascular system, your body can say, hey, we don't want this anymore. Let's secrete it. Number three, we're going to secrete it so that it can eventually be, number four, excreted. Okay. The kidneys carry out three basic processes. The sum of these processes determine the rate of excretion, With the exception of proteins, most substances in the plasma are filtered and enter the Bowman's capsule. Here's that Bowman's capsule. So the glomerulus, which is this cluster right here, glomerular capillaries, is the same thing as the glomerulus. This space is called the glomerular space. You have your afferent arteriole, look at the diameter, bringing blood in faster than it can exit through the efferent arteriole. As it comes in, you have these podocytes, which are these filtration cells that surround the glomerulus. And the podocytes create these little filtration slits that allow for only certain small particles to pass through to get into the first part called the proximal convoluted tubule. Okay, the glomerulus sits within the Bowman's capsule or the glomerular capsule. That's the very first part. So we have the glomerulus here, the glomerular capsule, also known as renal corpuscle or Bowman's capsule. Then we have the very first part that's convoluted, called the proximal convoluted tubule. And we have this loop, right? This is the loop of Henle, but since it's coming down in this direction, that's the descending limb. Here's the loop of Henle. Then it comes up, so we have the ascending limb of the loop of Henle. And then it gets convoluted again, that's your distal convoluted tubule. So this is what we have in here. And we can see part of it is in the cortex and some of it is in the medulla. Most nephrons, at least 80 to 85% of the nephrons are in the cortex. Maybe 15, 20% are located primarily in the medullary region, but the majority of the nephron is in the renal cortex. The main part that we see in the medulla is this part, the loop of Henle. The loops are here. That's where there's a lot of water and salt exchange. So this is a very, very salty area, the medulla. Okay, so again, just another picture. Again, it looks like a mess, but if we break it down and slow down a bit and go, okay, let's start here at the arcuate artery. That's the arcuate. Remember, the pyramid would be like that. So over the arc is the arcuate. Then there's an interlobar, and the interlobar, actually they call it an interlobular, but this is the other name for the cortical radiate artery. So the cortical radiate is the interlobular, not to be confused with interlobar. They're a little bit confusing. So in between two pyramids, right? That blood vessel that was here or here, that's the interlobar. Interlobular is the same thing as cortical radiate. So that's why you see here, think of this as the cortical radiate. And from that, you have the afferent arteriole coming in. Here's your Bowman's capsule. This is the beginning. This is your proximal convoluted tubule. And it's going to make a whole big mess, right? Then it's going to, if we follow it, it's going to come down like this in this direction. This is the descending limb. Here's the loop of Henle. Now it's the ascending limb of the loop. And now right here, this is the distal convoluted tubule. We see it here, distal convoluted tubule. But what I said in the earlier frame was that part of the distal convoluted tubule is so convoluted that part of it gets very, very close to that afferent and efferent arteriole, creating the cells of the juxtaglomerular complex. This is that part that's responsible for blood volume and blood pressure. Then we have still the distal convoluted tubule, and now we have these little connecting tubules, and all these connecting tubules lead to the collecting duct. Okay, so we had the proximal convoluted tubule, the distal convoluted tubule, and the loop of Henle. Remember, we had a descending limb and an ascending limb of the loop of Henle. And then let's keep in the back of our mind that parts of the distal convoluted tubule gets very, very close to here's the afferent arteriole, efferent arteriole, that's the glomerulus. But right in here, that's where the distal convoluted approximates and gets very, very close to regulate blood pressure and blood volume. That's the juxtaglomerular complex that I'm going to show you in a second. Okay, now different parts of the nephron is made up of different types of cells. Okay, just want to show you that this is the proximal convoluted tubule, and we have simple cuboidal epithelium there. At the descending limb and parts of the ascending limb, it's simple squamous. So you can see the different shapes of the cells are going to determine what it's permeable to. So like through this section here, this is going to allow lots of water and salt to kind of pass through this a little bit easier at that loop of Henle. Okay, so the different, and at the proximal convoluted tubule, the PCT, and the distal convoluted tubule, you're going to see these simple cuboidal cells. Simple cuboidal, simple cuboidal, simple cuboidal. They're found throughout the majority of the kidneys, of the nephron. Let's understand the difference between reabsorption and secretion. Reabsorption is when you can return the useful stuff back into circulation, whereas secrete is when the waste products that fail to enter the renal corpuscle through the filtration at the glomerulus. Okay, so reabsorption and secretion. Again, if this is, let's just take a section of the nephron, let's say it's the loop of Henle, and then let's create, this is just arteries and blood vessels surrounding it. We can have stuff that goes from here to here. That's reabsorption, number one. But you can have stuff that goes from the blood vessels into the loop of Henle, into the tubules, and that's going to be two, secretion. First, it's secreted before it's excreted. Okay, much of the filtrate is reabsorbed, especially water, glucose, some amino acids and ions. Secretion helps to manage the pH and to rid the body of toxic foreign substances. So secretion is first, and after secretion, it leads to excretion. What are we reabsorbing? In those peritubular capillaries, we can reabsorb sodium, water, glucose, amino acids. Some of the reabsorption is passive, but most of it is active, meaning active requires energy, ATP. And most of the reabsorption occurs at the PCT, the proximal convoluted tubule. That's where most reabsorption takes place. What materials are not reabsorbed? Urea, uric acid, and creatinine. These are the nitrogenous wastes, right? So when you break down amino acids, the amino acids have an amine group that have lots of nitrogen attached to it. It has to get rid of those excessive nitrogens and it forms urea, uric acid. The body has to get rid of those things. Some materials move from the capillaries into the renal tubules. That's secretion, hydrogen, potassium, drugs, creatinine. Materials that are left in the tubules will move towards the ureters. And from the ureters, it goes into the urinary bladder, and then from the urinary bladder into the urethra. Okay, so this is, if we look here, this section, that's the cortex of the pyramid. And down here, you could see medulla and cortex. So most of the tubular system lies in the cortex, but we could see the loop of Henle, where a lot of water and salt exchange takes place in the loop of Henle, in the medulla. So we have afferent arteriole, efferent arteriole, glomerulus, Bowman's capsule, proximal convoluted tubule, descending limb of the loop of Henle, ascending limb of the loop of Henle, distal convoluted tubule, a bunch of these connecting tubules, and the connectings lead to the collecting duct, right to the renal papilla. Minor calyx, major calyx, renal, pelvis, ureter. And at each of these sections in the boxes, you can see that there's like two-way arrows, right? So going from the blood into like poisons we want to get rid of, but maybe salt and bicarbonate and water we want to reabsorb. Salt we want to reabsorb. Some water we want to reabsorb. Okay, so the body finds a way to either reabsorb or to secrete and excrete things. So again, we can filter, reabsorb, secrete, or excrete. Right here at number 1, this is the filtrations. You have blood coming in through the afferent arteriole into the glomerulus. We pull things out that were filtered. That's the filtrate through filtration. Number 2, body's going, I don't want to get rid of it yet. Let's reabsorb it. That's number 2. We reabsorb. Then the body goes, all right, we reabsorbed enough. Let's secrete again. So it's going to push things back into the tubular system. Once it's secreted, we can, number 4, excrete. Now just take a look at how much is filtered, how much is reabsorbed, and how much the body can eventually excrete to become urine. So if you look at water, 180 liters is filtered, 178 is reabsorbed. We're only getting rid of 1.5 to 2 liters a day. Let's look at protein. Body's filtering 2 grams, about 1.9 is reabsorbed. So when we do urine tests, we don't want to see lots of protein being pushed out from the urine. If protein levels are high, there's a problem. Let's look at sodium. It's filtering 579 grams. We're reabsorbing 575, so we're just getting rid of 4 grams. Look at glucose. We're filtering 162 grams. We're reabsorbing 162 grams. How much should be in the urine? None. If you're spilling out sugar into the urine, well, that's an indication of diabetes. Okay. Let's look at creatinine. We're filtering 1.6 gram of creatinine. We don't want to reabsorb any. We want to be able to push it out. Okay. These are some of the hormones. Let's take a break and then I'll come back to these hormones.